Thank you everyone for coming. So this is the presentation of the result from the DESI DR2 analysis that was released to the archive well, yesterday night or tomorrow morning, depending on where you live. And well, I start thanking all the sponsors, participants of the DESI collaboration. So yeah, today there was a press release essentially saying the new DESI results strengthened hints that dark energy might evolve, and that was quite successful in hitting the press. So they are like just few examples. So that was today in the archive, these couple of papers that they are essentially the alphabetical papers that describe the DR2 results. There was also a bunch of papers that they were called DESI first author papers, that they were essentially non-alphabetical, and they provide like a supporting studies for the results presented in these papers. So yeah, this is like a summary of the DR2, the 3 years data release, and this is essentially a video for visualization on how the data looks like. So in DESI, we have essentially those 5 tracers: the bright galaxy sample, BGS, the LRG, luminous red galaxies, the ELG, the emission light galaxies, the quasars, and the Lyman alpha. So in total, this is essentially the largest 3D map released, well, not released, but analyzed today, which consists of 15 million galaxies and covers an effective volume of 42 gigaparsec cube. So let me just briefly describe the telescope, and then I will go to the science. So all the DESI instrument is located. So all the DESI science is based on the DESI instrument, which is located at the Kitt Peak telescope, the Mayal telescope at the Kitt Peak Observatory in Arizona. Is a 4-meter telescope, and essentially it consists of well, this is the picture of the telescope, and the new thing about it is not the telescope itself, but the DESI instrument, which essentially consists of this focal plane where we have 5,000 robotic positioners that they were essentially going to move the robotic fibers to capture the light of galaxies in each position of the space, and then this light is bring to the spectrograph, to the 10 spectrograph that they analyze, and they compose this light in essentially 3 channels, getting a like very accurate spectrum. So this is like an image of the robotic positioners. This is the image of the focal plane with the 5,000 robotic positioners, that they are just these things here that they can move. I will show just a video in 1 second. And they capture the light. So they can move to essentially point to the galaxy in that region of the sky where the telescope is observing, and then capture the light. This is just an example with a very nearby galaxy. I think this is M31, the Triangle Galaxy, if I'm not wrong. There is another photo with Andromeda, which is way larger, but then you see here, and then you see here which positioners they essentially capture the light. This is just as an example, because we are not typically observing that large galaxy. They are essentially, each of these fibers take the spectrum of just one single galaxy, but this is just an example from the nearby galaxy, right? And this is how you exactly, right? So for each of these 4 robotic fibers, then you capture the light, and then you recompose it in the whole spectrum to getting like a very accurate redshift accuracy, which will be used to essentially convert this redshift into a radial distance. So this is also an image of this 5,000 robot army positioners that conduct the light to the spectrograph, and they essentially each exposure time, it takes around 10 to 20 minutes, roughly speaking 15 minutes. And I believe this is a video of how it moves, so just to get an idea. So this is just like the center of the focal plane, and it's just like how positioners move to exactly match the galaxies that we aim to capture the light. This is another photo of one of the petals of the telescope and then you see here the positioners, and in the back then you see all the optical cables that just bring this signal to the spectrograph to decompose the light. Okay, so this is just at the instrument level. I won't say much about it because I want to center more in the data analysis and the cosmology interpretation of it. So that was the image of the sky we had in the analysis that we presented 1 year ago in the April 2024. That was corresponding to what we referred as DR1, the data release 1. And it corresponds essentially to 1 year of observation, essentially almost 12 months. Okay, and this is the North Galactic Cap, and this is the South Galactic Cap. So this in the middle is our galactic plane, and we don't observe through that region because of stars and clouds, and yeah, gas, stars, clouds, and we essentially only focus on the perpendicular directions, which are like what we refer as the southern part and then the northern. For each small circle, which is like the position when the focal plane really observe the sky, then we have to do like several passes because we have like a quite dense amount of galaxies there. So the more passive we have, like the more complete we have information about that region of the sky. So this is like represented with these colors here. So the red and the color is like the more information we have, the more the complete, what we call the completeness, right? And then we make up to 5 or 7 passes depending on the type of galaxy we're observing. So that was the situation on April 2024 on the DR1 results that we already presented here. This is corresponding to the DR2. There's a mistake here. To the DR2, which corresponds to the first 3 years of observation. And that was essentially the observations performed until May 2024. And this is the status 1 month ago. This is from February 2025. So this is not released, but this is the status of the observation. So already we have completed almost everything. It's like 86% of the nominal footprint has been already complete. And this is like another summary of the data set. So the year 1 corresponding to 1 year was released on April 2024 and corresponds to observations from essentially mid-21 to mid-22. Released today, it's 3 years of observation from 21 to 24. And we are already have almost the 5 3 years in time. So this is like the nominal time from the end of the survey, 5 years, which would correspond to the next data release, which is year 3. But we already are granted an extension of DESI of 2 extra years, 2.5 extra years, that will correspond to an extra data release that we probably will call DR4. It's still not clear whether they will be split in 2 or not. Going to the cryptic names of galaxies, bright galaxy sample, LRGs, luminous red galaxies, ERGs, emission-like galaxies, QSOs, quasars. So this is essentially telling you the number density of galaxies is a function of redshift, a function of distance, a function of back in time. And when you see here that the bright, the close have like a larger density, and then as we move back, then we have LRGs and ELGs that they have a slightly less density, and then quasars that is like a very sparse sample. So that was like the summary of the papers we had for the DR1. So this was the papers released in April 2024, and that was about the BAO of DR1. Back in November, we already released an extra analysis on this same DR1 data by performing what we referred as full shape, which is focusing not only on the BAO signal in the 2-point correlation function, but also in the full shape of the correlation function. And using that, we can get a bit more information, especially on the perturbation level. But here, what we are going to do is just update this BAO analysis and upgrade it from DR1 to DR2 with just more data. And this is what we are going to be describing today. I'm not going to talk about full shape analysis of DR2 because we haven't done it yet, and it will take a few more months to do so. So we know that distances in astrophysics and cosmology are hard. And in order to essentially infer the distance to an object, we need calibrators, right? So we can use essentially 2 ways. One is the standard candles, which is what supernovae does. And this is how the accelerated expansion of the universe was discovered at the end of the 20th century. But another way is also to use standard rulers, which it relies on a known size of an object or a known size of a feature that we can detect and use to essentially say how far away this object is. So if we know the angular size of something that we see over there in the sky, just by measuring the angular and the radial distance of this object, then we can infer the distance if we know how the universe has been expanded. But that's something that's a look for. So I've shown this plot or this animation very often. So what we are going to see here is essentially the BO, the baryonic acoustic oscillation, is a process that is produced in the early universe before recombination. It's a pressure wave that travels through the universe up to a point that the universe becomes transparent and it cannot travel anymore. There is a decoupling between photons and baryons, and that essentially sets a distance of the wavelength of the sound wave that have been traveling, and that distance is what we are going to use as a standard ruler. So this is what this animation says. So we have this expanding sound wave in the early universe up to the moment of recombination, where the sound wave cannot travel anymore. That creates like a set of perturbation regions. And around those perturbation regions, way later than recombination, then the galaxies end up forming. But these galaxies form in regions where this signature of this sound wave get imprinted. And this is essentially what we aim to detect by observing this 3D galaxy map. So when we do is just to do this two-point correlation function of this histogram of distances of galaxies. So making this histogram, then there is this particular separation when the probability of finding two galaxies is slightly higher than what you would naively expect. And that excess of probability in the two-point correlation function is what allows us to detect the BO and infer the sound horizon scale at that epoch. So essentially what we are going to do is to do this exercise of doing this two-point correlation function at different galaxy samples. And with that, then we can calibrate our distance and then make the Hubble diagram velocity versus distance at a function of time as a function of distance. So we can do this game in slightly two different ways. So typically the way we do is we choose, and we observe angles and redshifts. So we in principle cannot calculate these two-point correlation functions because we need distances. So the first thing to do is to convert this redshift into distances. But in order to do that, then we assume a cosmology. So you might think that we are cheating because we assume a cosmology to get distances, and then we compute something, and then we have been imprinted what we have assumed. But the way we do it is not like that. So it's true that we assume a fiducial cosmology to make the actual catalog in terms of 3D distances. And this allows us to essentially look at the BO scale in two different directions, along the line of sight and across the line of sight. So we know that if we were changing this fiducial cosmology to convert redshift into distances, and we know that the universe has to be isotrope, what we are doing is we are creating an fake anisotropy into that, right? So the idea is that knowing that the BO has to be isotrope and that the BO has to be like the same at different redshift, you can think of like doing a lot of trial and errors with creating this fiducial cosmology until you get a cosmology where your BO is perfectly isotrope along and across the line of sight and the same at different redshift bits, right? In practice, we don't do like that. What we do is we introduce two parameters that we marginalize over. And these parameters essentially account for these anisotropy distortions that they are known as the Alko-Paczynski effect. So we can do this independently for all the scales, but in particular, what we are doing here is we are focusing on the distortions that this anisotropy creates on one particular scale, which is the BO scale. A bit more for the people who are more into that, what this radial BO distance constraint is this angular diameter, it is radial distance, dh, which is nothing but essentially 1 over the Hubble parameter at a given redshift in units of the sound horizon scale. That in principle, we can assume it's unknown. We will see later how we can put units on that. And the same for the other BO direction, the direction across the line of sight. In that case, we constrain dm, which is the angular diameter distance, in units of the sound horizon scale. So we have these two dilation scales that we are going to play. This is one way of seeing this dilation. The other way is just you rethink these distortions in another base, and then instead of distorting along and across, then you can think of like an isotropic distortion, and that essentially conserve the scale. So the along and across the line of sight is the same, and like a warp distortion, which is essentially the Alko-Paczynski effect, that it conserves the surface of this sphere, but just stretches into direction. You can reparameterize in terms of these units, and then you create like a new isotropic distance, which is sometimes referred as dV, which is results of this combination, and something related to the Alto-Paczynski parameter, which is essentially the ratio of the two dilation scales. So just as an example, and this is still not new data, this is coming from the old DR1 data, you can do several things using this. So in principle, we've talked about this sun horizon scale, RD, that if it's known, well, that's fine. But you can do a lot of physics still being agnostic about RD. So the only thing you assume is that RD exists, that is isotropic, and it doesn't change with scale. So in principle, you can think of like taking like all the possible ratios between these distances. In principle, I have chosen here the like the isotropic distances at different redshifts is independent of this sun horizon scale, because essentially cancels out, and also the Alto-Paczynski at a given redshift is also independent of this sun horizon scale. So these sets are like a lot of cosmology constraint, and in principle, if you assume that the universe is lambda CDM, using this you can constrain omega matter without any assumption on the sun horizon scale value or on the physics of the sun horizon scale. Only that the sun horizon scale exists, that is isotropic, and it doesn't change with redshift. In addition to that, you get as well H naught in units of this unknown RD. So if you have a way to calibrate your map and give physical units to RD in megaparsecs, then you can break this and get a value for H naught and obviously RD. So this is typically used by informing the BEO with a BBN prior, which gives you information on omega baryon. And also assuming that you know early time physics, then you can get, which is the derived value for RD, and then break this degenerate. So another unfair advantage of the BEO is that you can do this at different redshifts. Here I'm putting just traces, but in reality, what is important is that this is like something nearby to us, and this is something very far away to us. So in this plane of these two variables, and this is just for lambda CDM as an example, you see that this degeneration direction rotates as we move in redshift. So by using a lot of redshift, then we have this unfair advantage that you can break all these nasty degeneracy directions and get something which is very precise. And this is why the BEO can get so much good error bars on omega matter and H naught. Now for the new thing, BEO DR2 results. So this is like the measurement of the BEO signal on the closest redshift beams, the bright galaxy sample at effective redshift of roughly speaking 0.3. So this is like the monopole signal. It's like the isotrope distortion. Do you remember just the isotropic distortion of the BEO? And this is like the quadrupole, which is like isotrope plus an isotrope. So it's not exactly Alto-Paczynski, but contains some information extra on the anisotropy. So this is on the BGS. You see like a very strong detection of the peak. Now you have the first LRG beam at redshift 0.5. The second LRG beam at redshift 0.7. Then a combined sample between the third LRG beam at the first ELG beam, which is at redshift, roughly speaking, 1. Another further away redshift beam on the second beam of ELGs at redshift 1.3. Then the quasar sample at redshift 1.5 almost, and then the Lyman alpha. So we have 1, 2, 3, 4, 5, 6, 7 redshift beams that we are going to use to essentially measure these distortions. And this is what is shown in this plot. So I've just put you to remind you, this is isotropic dilation of this dV. This is purely Alto-Paczynski, so perpendicular to radial. And this is essentially the same, but rethinked in this other base. This is across the line of sight, and this is along the line of sight. So the information in these two is equivalent to the information in these two. Okay, it's not more information, it's just the way of seeing it. Okay, so let me guide your eye a bit here. Field error bars is like the new data release, the DR2, and the empty ones is that the old one. So the new one contains the old one. So they are correlated. And in principle, you might think they are perfectly correlated because the analysis, it's very similar. So you see that the points have been moving a bit, but that's like a statistical fluctuation. So we expect that because the universe is stochastic, one realization is just a random realization of the universe and it contains some noise. And when we are more data, this noise can get reduced. And the different lines, this is in black, is like the best fit lambda CDM cosmology to the DESI data alone. And this is shown as a straight line because it has been normalized by that, by definition. And this other line is the best fit Planck cosmology, assuming lambda CDM. So you see these are different. How different they are? Well, we will see. So there are a few things maybe that we need to highlight here. First, that was in year one, we had this sort of strange point here that was creating like a big Alko-Paczynski effect on that low redshift rim, that it was not compatible in principle with any model. And that was like something strange. With more data, this thing has gone down. So it suggested that indeed that point was a statistical fluke. And one would expect that with more data, this will still keep going down to something around here because there are essentially no models in cosmology that predicts this Alko-Paczynski parameter at that redshift time. So another thing that was important, it was that this point here was quite low compared to the Planck prediction, was like more than 2 sigma, a bit more than 2 sigma away. It has gone up with more data, but the error bars also are like smaller. So in the end, we are still like quite discrepant with Planck at that point. That point, like there were like a lot of complaints, especially because that point was also a bit in tension with the previous measurement from SDSS. And this is what is shown here. This is just corresponding to this point in this base in DH and DM. So that was like the old BOS measurement was here, and that was the DESI data. And then they were saying, well, these maybe are too discrepant because they are somehow correlated. But what we have checked is that adding more data, even this point hasn't moved much with respect to Planck. Where it has been done is just more in agreement with the previous BOS measurement. So these suspicions that this point was something wrong between DESI and BOS, this has been essentially gone away. Okay, so that's essentially the raw measurements in terms of distances. But here we haven't assumed yet any cosmological interpretation. This is just radial distances and angular distances in units of the sun horizon scale. Let's go to the interpretation. So let's start with the lambda CDM model. So now we think of these points in terms on lambda CDM, and this is like the updated plot I showed you before the old plot, and this is like the new data. So you again see how these different redshifts like shift the alignments in these two parameter space. And what we get from DESI data alone is this value for omega matter, like very precise, of 0.2975. If we calibrate our system adding information on the baryon density, we can get information on RD, sorry, and then we can break this degeneracy and get a measurement of H, independent of any CMB data, but not independent on pre-recombination physics. So we are assuming pre-recombination physics in this thing, and we get a value of H naught of 68.5 plus minus 0.6, roughly speaking. We can add also some extra data set, and this is this theta star. This theta star is just another BO point. So this is just the angular BO on the surface of the CMB, okay? And this is just minimal information on CMB because it's just the angle, and this is very well measured. Let's take a look at how this compares to what the CMB data tells us using Planck on lambda CDM model. So we have here the old DR1 BO data, and now with the new DESI DR2, then these contours have essentially shrink, but they are like very centered. So adding more data just haven't shift things in lambda CDM. It's like the lambda CDM model essentially like the same, we just have more precision. And this CMB point here is essentially Planck. And we see here that there's a bit discrepancy, okay? So we have quantified this discrepancy, and by CMB, I mean Planck, temperature polarization, and some Atacama Cosmology Telescope data for high Ls and lensing reconstruction, right? So just for the information. But essentially, there are like this discrepancy on the assumption of lambda CDM of 2.3 sigma, okay? That's nothing big, but it's something that is there. And this is without any calibration, because you see here, I haven't used BBN yet on this. I just have assumed lambda CDM. So if you exclude lensing, that 2.3 goes down to 2. So, and it was already 1.9 for DR1. And if you calibrate your system, you add information on BBN, and DESI plus BBN plus the angular BO, it's, well, a bit discrepant with Planck, but still consistent, okay? So that's something interesting. Let's look at another interesting thing within lambda CDM yet, which is the comparison to the supernovae, calibrated and uncalibrated, okay? If we look at the calibrated supernovae, we see that we still have like a high discrepancy on H naught. This is not new. We already knew from BOS that this was going to happen. And now we can quantify this tension in 4.5, okay? So it doesn't matter whether you split DESI in higher redshifts or lower redshifts, both are very consistent, right? So this is splitting the DESI BO data in something above redshift 1 and below redshift 1, just to check consistency, and both are like essentially crossing at the same time, at the same position. And this is just my telling us that there is new physics at the early universe that change the value of RD. So this BBN plus assumptions of pre-recombination physics is wrong, or that there is some problem with the Schultz calibration. So essentially that there is a problem with this or with this. Another thing you can do is just, okay, forget about the calibration, right? I just work with uncalibrated BO, uncalibrated supernovae. So now I can compare them, because in principle, without calibration, you are just tracing the expansion history, the uncalibrated expansion history. And this is informing, as I was telling before, on omega matter, okay? And the funny thing here is that there is a mild discrepancy on the omega matter parameters between supernovae and BO. And this is not about the calibration, because omega matter is independent of calibration. So if you use Pantheon, this discrepancy is nothing, it's 1.7. With Union 3, it's 2.1. Not important. But with the DES supernovae, it's almost 3 sigma. Okay, so this hints like a new problem with the omega matter value within lambda CDM. So you heard about the WOA model. Okay, so for the people who don't know, very fast summary. Lambda CDM model, we assume that dark energy is a cosmological constant. So the equation of the state is fixed and it's -1, right? So a toy model to relax this assumption is what is called the WCDM model, that you say, okay, dark energy is not a cosmological constant. It's something, but it has an equation of a state that is fixed. You require that it's small, because otherwise we wouldn't create acceleration, but it's fixed at any redshift. So this extra W, not WA model, is just a toy model for parametrizing the time evolving equation of a state. So now equation of a state is not only different than -1, but it also can change with time. And this is the way it's parameterized. Okay, there might be other ways to explore, but we just choose this model for simplicity. And as you know, we already had issues when we were working on this model. So this is the parameterization of these two parameters, the W naught and WA. And when you combine DESI plus CMB in this region parameter space, you already see that when you combine with the full CMB information, this hints for a 3.1 sigma tension with lambda CDM. So the lambda CDM point is when W naught is -1 and WA is 0. So if we open that parameter space, DESI with CMB has a 3 sigma preference for non-lambda CDM. And when we add supernovae information, then this changes. Well, with Pantheon, decreases a bit, but this stays around 3. And with Union 3 and DES, it goes almost up to 4. So now this is interesting, and Exactly. So the new thing is that without supernovae, there is already 3 sigma. And let's dig a bit more into this. So what happened with this 3 sigma? This is from the full CMB data. So what we've done is just to essentially remove things on the CMB and then see how this changes, right? So if we remove the lensing part of the CMB, it reduces a bit. So the ellipse grows a bit towards that direction, but the ellipse essentially is not shifting. So it essentially stays in the same place and just grows. And another thing you can do is also like to even reduce more the CMB information, right? So you have 3 sigma, now you have 2.7 sigma without lensing. DESI alone, it doesn't do anything. So it's like principal compatible, 1.7, that's nothing. DESI with just the angular BAO from CMB also is very consistent. I don't have the number, unfortunately, but from the plot you see here that is well within. And when you start adding this minimal CMB information, which is just the information on the physical baryon density and physical baryon plus cold dark matter density from CMB, obviously taking into account that they are correlated and everything, we can make it up to 2.4 sigma. So this is like DESI plus minimal CMB information, and this is 2.4. But again, you see that the ellipses don't shift. So there's nothing like wrong, especially wrong with the CMB that is making the ellipse flip when you turn it on and off. We just like make it a bit more, but the ellipse is always centered in that specific direction. So another interesting exercise we can do is to look at the supernovae sample. So this is what happened with the supernovae sample. In principle, we're just taking the DES supernovae sample. And if we remove the supernovae below redshift 0.1, then the significance also reduces quite a bit, but the ellipse still doesn't move. So you may wonder why to remove exactly those supernovae. So it turns out that the DES supernovae program is the most homogeneous one across the 3, but except for those supernovae below 0.1. So the supernovae below 0.1, they containing supernovae from a mix historical programs that they have like different calibrations and different fittings, whereas only the supernovae above 0.1 are those coming from the DES, and they are like belong to the most homogeneous one. So you may think that these are like the most trustable or the less sensitive to have error calibrations, or they have like spurious effect. But still, I mean, removing these, obviously the significance reduces a lot, but the ellipse doesn't move. So again, and what you also, another exercise you can do is just to combine DESI BAO and use the DS year 3.2 point function. So this is using DS information, but not a supernovae, but on the galaxy, shear, galaxy, and shear information. This is called the 3 times 2 point function. And with that, essentially gravitational lensing information, without CMB, you already get 2.2. So again, even without CMB and without supernovae, you get something along always that direction. So this hints something that it might be there. So let's talk about neutrinos. So BAO in combination with something can measure the sum of the mass of the neutrinos under an assumption of a model. Okay, so let's start with lambda CDM. We know that lambda CDM have problems, but just for simplicity, start with lambda CDM. So DESI BAO alone doesn't constrain the mass of the neutrinos, but in combination with CMB, it does. What we have observed is that depending on the exactly likelihood software we use, there is a slight change, and this is because the different likelihoods tend to have a different treatment of the lensing power of the CMB. As a fiducial, we have used something called CAMSPEC, but there are these other two, the PLIC and the lollipop kilipop likelihood that gives slightly different power. So they take the results as a grain of salt. And using this CAMSPEC, what we get is a 2 sigma level, an upper bound very close to the 0.06 bound from the neutrino oscillations. The thing is, in principle, we put a physical prior on imposing that the sum of the mass of the neutrinos have to be positive. But if you relax this prior, then the profile likelihood of this constraint, it will peak at negative masses, okay? And if you allow this to peak at negative masses, then this hints like a 3 sigma tension with the constraint from the terrestrial experiment. Okay, but it allows to decrease the tension on omega matter that lambda CDM had with BAO in Planck. So you see this because omega matter and the sum of the neutrino masses are correlated. So if you allow the CMB to go below this line and go to the negative neutrino masses, then the agreement with DESI data it's better because DESI wants something here, Planck wants something over here, so they will cross here. So they will reduce this tension. Obviously, if we are like favoring this evolving dark energy model, then it makes sense also to look at the constraint of the neutrino masses under the assumption of this model. And this is how the picture looks like. So DESI alone doesn't do anything, but adding CMB and adding supernovae, then these neutrino masses are better constrained. So in that way, in that case, the posterior now peaks on the positive sides, even if we relax the positive mass prior. Okay, and this is the value we get at 95%. Okay, and something 0.13 if we are adding the supernovae data. But in that case, things are better behaved. The tensions are really relaxed, and we don't have that issue with the neutrino masses and also the tension with the omega. So just a summary, and I'm just finishing here. So this is like the conclusion. So the takeaway message is that DESI alone is really consistent with lambda CDM model. But this lambda CDM model seems to be slightly different than the lambda CDM model that Planck's won. It's like 2.3 discrepant, and it can be reduced if you just relax lensing and things like that. If you allow varying dark energy model, there's W not WA, then the DESI with CMB is in 3.1 mild tension with lambda CDM. And this is essentially because of the tension you were observing on omega matter. So with this evolving dark energy, what you are doing is you are relaxing this tension that Planck and lambda CDM had in lambda CDM. Okay. With supernovae, this grows from essentially almost 3 to 4, depending on the supernova samples you use. But remember that essentially this is essentially driven by the low redshift supernovae, although the tension is reduced, the center of the lift doesn't move. And for the neutrinos, we get this constraint of less than an upper bound of 0.064 at 2 sigma for the DESI with CMB in lambda CDM, peaking at negative neutrino masses if there are no prior, and something of around 0.16 at 2 sigma with the W not WA CDM model, and now with the likelihood peaking at the positives. And just the last picture, and that's all. Thank you very much.